talking about the work, I want to show you who did the work. So there was a number of people that I will highlight throughout the talk that are shown in these pictures here that have done the work. So I'm the one sitting at the desk and not being able to use the microscope or program as much anymore. But yeah, thanks to all these people that did the work. And again, I will introduce them when time comes. Just to explain what we do in our group. So we, oops, oh, it was a bit slow here. What we do in our group, we work on, just a second. Okay, we work on several things that try to then come together and actually explore this subject here, and that is structure research. That means exploring the structure of materials and in particular the atomic structure, but also the electronic structure. And for that, we develop instruments. We, of course, purchase also instruments that are commercially provided. We modify them. We develop reconstruction algorithms, and I will focus mostly on those today. But also, of course, it includes modeling experimental data so that we can then compare what we measure with what we would expect from theoretical predictions, in particular predictions made by colleagues that do ab initio calculations. I'll show actually one example of how we do this comparison. You've heard a lot about electron microscopes already this week, and I think this is a very interesting format, this conference, of bringing really together the mathematicians and also the ones that are more on the applied science side and really converging and using basically the best of both worlds and trying to get this together. That's actually a very nice initiative. So thank you very much for doing this. So these electron microscopes have a lot of parameters. I recently learned that, for example, one of our instruments has more than 500 different power supplies where you can adjust all kinds of lenses, multipoles, and so on. So this is really very complex, and this is an oversimplified, if you want, schematic of it. But it shows that you can, even with these very few elements, you can already do a lot. You can massage the beam, you can change the focus of what you see on the detector, imaging different planes on it. And if you want to explore atomic structure, you can do this also in many different ways. I mean, many of these you have already heard about yesterday. And I guess you will hear more about today. But for example, you don't always need to show the atomic structure. That means atom by atom. If you want to, for example, only know how much are these atoms displaced from their original lattice side. For example, if you have strain, like in this case here, and that, of course, then gives you another advantage in that you can really enlarge your field of view. So you can have several hundred of nanometers with maps of how much these atoms actually deviate from their original lattice site position, or the gradient of that, which is the strain. But of course, you can also do direct imaging of atomic structure. You can also image electric and also magnetic fields in principle at this atomic resolution. You can try to really reduce those and when you want to observe very fragile structures. And of course, in principle, you can also go to 3D in atomic structure. And all these you have heard examples of already, and we'll probably hear more about in this during this week. See, my system is a bit slow here, but yeah, hopefully it will work. So now imagine you have this electron microscope here, and it has this detector down here, and these detectors, it doesn't have to be the detector at the end of the microscope, it can also be other detectors that, for example, record EDX spectra, but you can then acquire a lot of different types of information from this microscope, which you can then make use of. And again, I mean, a number of these you've heard of already, and I will just touch on a few of these. In principle, this is the principle that you are after, and that is acquiring data. Maybe you want to reduce the data, and so you may have to reduce the data because it's very much. and you don't need all this data because there is a redundancy in it. And then you apply some reconstruction algorithm to recover your atomic structure. And in the process of that, you also apply some constraints, which ideally are very physically reasonable and don't somehow over-constrain your problem. And these could, for example, be sparseness in some domain, atomicity. Of course, we know that matter is made of atoms. And it may also be something very abstract, like, for example, the consistency with some dictionary that you build by exploring more and more experimental data, or that is built by using data from other sources. Could also be, for example, that you use a database of lots of data collected by different labs, and I will actually come to that at the very end. So here's the outline of what I'm going to talk about. I first want to talk a little bit about constrained focal series reconstruction or inline holography. Then also mapping 4D STEM at low voltages, especially of 2D materials, because there you really want to get enhanced scattering at these low voltages. And then also doing some ptychography and basically presenting our perspective on ptychography. And then again, as I already indicated, what is next? I mean, where do we want to go next? But I'll say more about this when I come to this point. First, let me talk about this inline holography. So remember this definition of the problem in the previous slide, that we acquire data and then we have some reconstruction algorithm, and this reconstruction algorithm also includes some constraints. So here is a reconstruction of some microscopy data that was acquired without an electron beam, but just with light. So this is a simple optical microscope, and what you see up here is not the atomic structure of something very strange, but it's on a much larger scale. Namely, if you look at the scale bar here, this is a 10 micron scale bar. These are just cells, live cells in a liquid. And if you record a focused image, you don't see anything. If you defocus more, you actually see much more contrast. And then if you apply some reconstruction algorithm, you don't see much more. If you only look at the amplitude, that means the absorption, but then the phase shift is what actually contains all the information that you're after. And now you can really see what these cells are made of, and you can get a much better picture of these. So that is the concept of this inline holography or focal series reconstruction that I'm going to talk about now, but applying this to electron microscopy. And if you acquire a focal series, for example, these are now iron core filled carbon nanostructures that TEM Ostoikeskin-Mora has acquired some data of. And what you can see here, you can nicely see the atomic structure. Well, yeah, you can see there is some maybe not atomic resolution, but you can see somehow there are some layers of this carbon material. But there's something missing. And it is actually that the gray levels inside the material somehow vary, and they're roughly the same as outside. And you would expect outside to be vacuum, so there should be actually a phase shift relative to what's inside. And that is just missing in this picture because the low spatial frequencies are missing. And I don't know how many of you are familiar with coherent diffractive imaging, but there's also a technique that is not applying a compact support to it, but if you just want to recover the crystal structure from diffraction patterns, there's this algorithm called charge flipping, which finds some application also in CDI, so coherent diffractive imaging, but is also in the field of crystallography quite common. It somehow is used, I believe, more frequently now than direct methods and the old established techniques. And applying this now, this flipping, not just to the density or the charge or the potential in our case, but to the gradient of that, allows us to then really somehow add information that was not extractable from the data. So the agreement of this potential map here with the data is the same actually as the agreement of the original potential map with the data. So we can now apply constraints to somehow help us add information that was not really available from the data directly. It's a bit like the missing wedge, like we heard yesterday also, the missing wedge problem in tomography. There is data that you didn't acquire, and somehow you now have to make up for this missing information because it produces artifacts otherwise. In tomography, it produces these elongations along the z direction. In focus series reconstruction, it means that you have missing low spatial frequencies, which you want to recover to make your data more physically reasonable, if you like. And this is just another example at atomic resolution, because of course this talk is about atomic structure. So if you see now here on the left-hand side, you can see this is just a simple nonlinear reconstruction algorithm that reconstructs the phase from a focus series. And you can see nicely these lattice planes here, and this is what many people are happy with. But what is missing here is actually that the low spatial frequencies are not in this at all. You can also see this in the Fourier transform. There's actually a black hole in the center, and that just indicates that low spatial frequencies have not been reconstructed at all. This is already different here. This stands for full resolution inline holography. It actually uses some it combines different algorithms together and uses the strength of, for example, this transport of intensity equation to actually extrapolate to low spatial frequencies, and uses some version of that to also then help extrapolate to low spatial frequencies. And now you can see this black hole is gone, and a lot of the low spatial frequencies have come back, but there's this problem with the transport of intensity equation that it actually then also enhances noise at low spatial frequencies, and then applying this regularization actually now gives a more reasonable reconstruction. There may still be some artifacts here and there that have not been put away with, but at least the reconstruction now has improved a lot. And these lattice planes that you saw in the original reconstruction, if you look at the FFT, they're still there. And you can also see them in the image. So they're still there. It's just because you now recover all the information, you now have also a realistic balance of the high and the low spatial frequencies. And you really need to actually adjust your contrast in order to see them better. But that is actually a more truthful reconstruction, because you now have all the information. It's always a question whether you want all the information or whether you want to highlight certain information. And that is, of course, at least from my perspective, it's not really the task of the algorithm to decide, but you can still afterwards do some high-pass filtering of the reconstruction to get what you want. Or maybe you want to have a low-pass filtered reconstruction in order to recover other information that you might have been after. Here is just an application also to some carbon nanotube at very low voltage. So this is only at 40 kilovolts. This is in the Salve microscope at Ulm University. So this is a microscope that has a spherical and chromatic aberration corrector.
Sorry, Christoph, there is a question from the audience here.
Yeah. Can you return on the previous slide? I want to ask why you think that actually this regularized image is better than the other one, because it seems like you're losing some information there. So what are you gaining? I see it's smoother as an image, but that doesn't mean you have all the information from the other one.
Yeah, what do you gain? That is a very good question. Thank you very much for asking. If you look at the Fourier transform of it, you can see that the high spatial frequency information, that means the crystallographic information, has not been lost. Right? So you still have, if you look at the Fourier transform, you still have all these diffraction spots in the Fourier transform of this image. That means this information is there. You didn't lose anything. However, you gained now, you get a more truthful representation of the phase shift. So if you look at this reconstruction over here, that may be more, it may be more easily and directly interpretable, but it's only half the truth. So you can take this one here and apply some high-pass filtering to it and get something that looks like this again, if you really want. But you may also be after very different information. For example, you may want to know something about the thickness of your sample, which is proportional to the to the phase shift that you see here, because the phase shift is actually proportional to the mean inner potential multiplied by the thickness of the sample. That information is absolutely lost in this case, but it is retrievable here. So you can now, once you have this full information, still decide what you want to do with it. And that is why I showed this. You can still see the lattice planes here, but you may have to apply some filtering to get back or to get something that looks like this, where you can see them more easily, but you have more information. It's like, you know, on your stereo, if you only turn on the treble and always turn the bass and the basically medium frequencies to 0, you can still understand what people say in the radio, but you don't have the full truth, right? You only have some information.
Thank you.
You're welcome. So here is, that's what I wanted to show. I mean, from this focus series here, where you can really see, because electrons are very coherent, you get large delocalization, but this delocalization is actually important in order to recover the phase shift of the electrons relative to, for example, the vacuum wave, but also to each other, because this focus series reconstruction, this nonlinear one, actually treats the interference between all the electrons that interfere with one another, not just interference with some undiffracted beam. And you can see now all this very convolved information can then be actually be covered and recovers basically the phase shift inside the sample. And if you zoom in, you can now see really it also recovers the atomic resolution structure of this double-walled nanotube, despite the fact that your wavelength is actually quite long. So because you have a very low accelerating voltage. And this data was actually provided by colleagues in Ulm, it was not required by our own. But coming now to low voltage, that was a very special microscope, which was a TEM. But now we want to go more into the business of scanning, as has been very much a current trend, actually, that scanning transmission electron microscopy seems to be really much more preferred over wide field illumination microscopy in TEM. So this is a scanning electron microscope that operates. It operates at low voltages. So this is has a maximum of 30 kilovolt, and it can go down to, let's say, 1 kilovolt and even less. So this is just an SEM. So it's not intended to be a TEM. It's not made as stable, but we're working on that to actually get also atomic resolution from it. I cannot show that yet to you, but even without going to atomic resolution, you can still do a lot with these instruments. For example, you can, because you have so much space inside, you can now build special diffraction stages where you can have a camera that you put in yourself, and this can also physically change the camera length. You can see now the camera length is shortened because the camera is moved closer to the sample, and the sample sits right here, and the electron beam comes through this pole piece right here. And you can see how when you change the camera length, the size of the diffraction pattern actually physically changes. You can also tilt, because this is now a 6-axis goniometer. You can tilt the sample. You can recover, for example, 3-dimensional diffraction information. Because you have such low voltage and you can really control your dose very nicely, you can now also record diffraction patterns from very beam-sensitive materials like these MOFs. And when we now scan across our sample, we get something like 4D stem information in the TEM, except that maybe the size of the spot on the sample is a bit larger. And if we do a setup like this, that's what we typically do. We focus the diffraction spots on the sample. We probably shouldn't call it 4D stem. I learned recently that now we are supposed to call this scanning confocal electron diffraction. That means SCED, very similar to scanning confocal electron microscopy, but in diffraction mapping, because you focus the diffracted beam on the detector and illuminate a larger area on your sample, which doesn't, of course, it reduces your resolution, but it also reduces the dose on the sample, and that may be advantageous for beam-sensitive materials. So just to show, and then I will stop with the hardware, you can also do this with direct electron detectors. So this is one of these Medipix detectors, which can go to very high frame rates, for example, 23,000 frames per second if you reduce your bit depth to only 1 bit, And if you scan very fast, I guess this, at least in some labs, this has been shown to be sufficient because you don't get so many electrons. But that's just to show that this can also be done inside an SEM, which gives you now the advantage of having very low noise, actually no readout noise of your detector, and just the Poisson noise that you model with most of your statistics assumptions anyway. So just to show what this instrument can do, also determining atomic structure, because that is often, you don't need to know the position of every atom. You just need to know in principle the diffraction pattern and how these change as a function of position. So these are two layers of graphene that overlap in some region, where now you have a twisted bilayer in this place. And you can see if you record a diffraction pattern from this area, it is a single layer graphene. If you record it from that area here, it's a single layer graphene. And if you record it in the overlap region, you can see the twist angle between the two layers that are superimposed here. And this can be done, of course, also, for example, with MOS2 and graphene or different stacks of 2D materials. And you can really characterize these without having to go to a TEM and without having to spend very high dose on your sample, which reduces also, of course, the damage and allows you to really plan your experiment for the TEM without having damaged it too much beforehand. And for example, if you buy one of these twisted bilayer graphene materials, as we did here, this is a commercial sample, and you have to be careful. They may tell you, oh, this material has, for example, a twist angle of 8 degrees. Well, it doesn't quite, because you have many domains with different twist angles. Single domains here, as you can see, there's no double layer, but all the other ones here are 2 layers, and they have all kinds of twist angles between them. So if you don't look at it microscopically, you may not know really what you have when you do your experiment with these kind of materials. But going now from this SEM to a 200 kV instrument, which can also go down to 30 kV. This is now a neon Hermes, and we shortly after we purchased this, which is now nearly 3 years ago, or yeah, well, that is at least when it arrived. We also bought one of these direct detectors for this instrument. It's now not a Medipix, but a Dectris ELA detector, which is also one of these hybrid pixel detectors, and it can go up to 15,000 frames per second if you reduce the size, the area that you read out, and also if you reduce the bit depth from 16-bit to 8-bit. And the nice thing about this microscope, because the detector is mounted behind the spectrometer, you can also run the spectrometer as an energy filter and remove a lot of the inelastically scattered electrons between your dark spots, which means that you now have data that is somehow more easy to model, because you don't need to account for this inelastic background in it. And because it goes very fast, you can also do live processing of it. For example, this frame of 500 by 512 pixels on this detector is acquired in 17 seconds, and you can do live processing, for example, extract the center of mass and apply not only these masks, but also all kinds of other masks to the data on the fly, and then only store basically this reduced information. I will come back to this, which is actually quite advantageous for many applications if you don't need to store tens of gigabytes of data. So here Dectris also makes a faster detector that Benedict got to test at NEON. It's not installed on our microscope, but this now even runs up to more than 100,000 frames per second. So that means what took 17 seconds on our detector only now takes 2 seconds. And now you can really average also over multiple exposures, because it goes so fast. And you can then get the same kind of information, also the same kind of online data processing with much faster acquisition, which reduces, of course, distortions in your images, because you're not scanning over a moving target, but your target during the exposure is more likely to be stationary. And this is just something, when you go down in voltage, you get more strong scattering from thin materials. For example, this is the twisted bilayer of graphene. where when you scan very fast, you don't actually record so much information. The information is quite noisy, but you can then acquire multiple scans and really improve the signal so that even for this bilayer of graphene, you can get with a simple center of mass analysis of your data, really get very nice atomic resolution information about local atomic scale electric fields. And of course, if you take the divergence, you get something that is proportional to the charge density of this material, or the projected charge density. But now coming really to a topic that really requires more of the mathematics that is to be discussed in this workshop, at least from what I understand. And I think there's a lot that can be done. And hopefully there may be something where discussion is now spawned, and hopefully potentially also some collaboration in the future. So this is now ptychography. But before I get in this topic of ptychography, I just go back a few years to a paper that was written by Wouter van den Broek. So his aim was to reconstruct the atomic structure of something like this gold nanoparticle here, or see whether this can be done just from high resolution TEM images. And he found out actually there's enough information about the 3D structure of the position and the position of all these atoms if you tilt the sample, or in principle, you could even just do this by tilting the beam by only plus minus 10 degrees in both directions, in both alpha and also beta. So you don't need to have a full 360 or plus minus 70 or whatever tomographic tilt series. Plus minus 10 degrees is already enough to give you basically really a 3D reconstruction of this atomic structure if you include dynamical scattering in your reconstruction algorithm. And that is what he did is, this is really a simulation of the dynamical image. Like all these images are calculated, of course, with a multi-slice calculation. Whereas if you just do a kinematical approximation, the image looks very different, and you wouldn't be able to really get a quantitative agreement between the forward simulations of your from the model that you iteratively refine to the data that you record. So this is all in simulation only, and Colin has talked about this yesterday, that this is really tough to do actually if you want to do this experimentally. So I admit we also haven't really continued trying to do this experimentally yet, because ptychography also, as Colin has said, is actually quite powerful and contains even more information. But just to show, this is the approach that we took, basically taking a neural network approach without basically with a linear activation function. So I guess you shouldn't be calling it an artificial neural network, but just this the structure corresponds very nicely to the multiple scattering, and it then reconstructs the potential. And again, here we applied constraints to the reconstruction that we believe are physically reasonable. And the constraints that we've applied are that the L1 norm of the reduced potential is also minimized. So of course, as you know, this will lead to a peak reconstruction. But what do I mean by reduced potential? The reduced potential is the potential that ideally should only have delta functions. And if this reduced potential is then convolved by the atomic potential, because we know, of course, they're tabulated, the scattering factors of our atoms. And if you have multiple atomic species, you can still define a generalized atomic form factor, as is done, for example, also in direct methods that have been used to solve many crystal structures. So this is really well established, these generalized atomic form factors. But if you remove them from this potential here, you really get a delta function map of peaks. And to this, actually, the L1 norm can very nicely be applied. And especially when you do this in 3D, that means these are now 10 potential layers that have 2 angstrom distance between them. You also don't run into the problem of having overlapping atoms somehow. So the atoms are all nicely separated because you only look at 1 layer of atoms at a time. And this particle here was tilted so that you can see these are not each layer is 1 atomic layer of the sample because they're tilted, but you can see multiple layers, for example, in this case, multiple layers of this structure here correspond to a single layer of potential, which of course makes sense. You do still have limited resolution along the Z direction. That's why you don't see them fading in and out so nicely, but you can still, from these maps, you can still recover the position of all the atoms in 3D space. And of course, HRTEM is, as I've already indicated, is not maybe the best method for this. If we apply far-field ptychography, we acquire information to much higher scattering angles. And that, of course, contains also more 3D information. And so Wouter has then also in a follow-up paper in 2013 investigated now, for example, scanning, confocal electron microscopy, but also this now very popular far-field ptychography. And it was also popular back then, or it became popular, and has simulated now ptychography data, also again, while tilting the sample a bit and combining all this information at once. He was also able to recover the object potential. So not just the phase shift, also in the high resolution case, that was the same, I just didn't show that, but both the elastic scattering potential and also an absorptive part of the potential, that means an imaginary part of the potential, accounting for scattering outside of your detection system, or really exciting some inelastic excitations, which then, because you assume zero loss filtering, scatter outside the elastic channel and with that not into your recorded data anymore. So you can really recover this more than just the electrostatic potential using, of course, this technique, and also in 3D. But now that was all in simulation and long time ago, and back then we didn't have all the detectors to really do this as well as we can do it now. And before we had our own detector, we then collaborated with a group of Dave Muller, who gave us some data from this niobium chloride material, where the 2D reconstruction at the time did not reveal really the spacing between these atoms here. And so what we then did is we ran it through this multi-slice reconstruction algorithm, and applying also constraints. And in addition to applying constraints, we also tested if the data could be reduced. Do you really need all this data, these gigabytes of data, in order to do the reconstruction? So if we just apply a single slice and we set this mu parameter here, which is a weight on this L1 regularization of the potential to very small numbers. So let's say, for example, 10 to the minus 6, we basically have a non-regularized reconstruction, and we also really don't see this dumbbell here resolved. And even if we apply some regularization, it wouldn't be resolved. But if we then really, and Dave Muller has also shown this in multiple, and Zhen Chen and basically his group have shown this in multiple web presentations, that if you include multiple scattering, you can really not only have a three-dimensional reconstruction of your sample, but also your lateral resolution improves because the multiple scattering is more faithfully treated, so you get a much better agreement between your forward calculations from the current estimate of your model and the experimental data. But this paper, in addition to applying now, instead of 6 slices, and also increasing this regularization parameter, the data was now reduced in size. So instead of the full data, it was now binned by 3. So 3 binning by 3 in each dimension. And then also cropping only 12 by 12 pixels from the diffraction pattern, the center of the diffraction pattern. So this is now reducing the data set to 144 numbers per probe position, instead of this was recorded on the MPAT detector, so the 128 by 128 pixels beforehand. And it recovered really now the dumbbell spacing very nicely, and also showed that the data doesn't need to be as large as one would have assumed before. So reducing now the number of data, but also the dose on the sample a lot, would mean that you want to position your beam more over larger areas without having basically every probe position sample. And that is what now Marcel Schlotz in my group has tried now reducing really the number of probe positions. And this is a full reconstruction. This is experimental data of molybdenum disulfide, and reconstructing this. It's not iterative very long, so the atoms are not very point-like yet. But I think for demonstration purposes right now, this is actually sufficient. And the question is it possible to reduce the number of probe positions by a factor of 40 and still get a faithful reconstruction of all the atom positions? And well, the first thing that at least came to our mind was, well, we could do an interlaced scanning, but then you hit the atom. This somehow gives some more wave pattern with your atomic structure. So let's just try random scan positions. And if you do that, like we would, for example, do in some of the compressed sensing schemes, if you then do a reconstruction of only 1/40th of the beam positions, you don't really see all the atoms very well anymore. And the question is, can you improve on this? And so what Marcel has done is he has actually now trained a artificial neural network and basically used now a reinforcement learning scheme and feeding in the position of the beam, but also a compressed representation, like an auto-encoded representation of the reconstruction with the current estimates of probe positions, and try to then really improve or predict probe positions that have an improved reconstruction. And the figure of merit he was trying to optimize was the contrast in the reconstruction over what the current estimate was. And so basically he came up with a scheme where he first had some random scan of some area that he scanned randomly. And from this initial reconstruction over this first patch of probe positions, he then fed these together with the reconstruction, the probe positions, into this reinforcement learning scheme and had it then predict. It was before the experiment, this was trained on some test data. And then during the experiment, the only thing that this network needs to do is predict new positions. So this goes quite quickly. And then predict positions for the next patch along the way, and then use all this information to then predict the next patch and so on. And you can see here, the initial patch was reconstructed with random positions, but then using that information and the probe positions, he was then able, or the network was able to predict probe positions that led to a much improved reconstruction. And then at the end, you can see this is sort of consistent. At least all the atoms are being found, whereas if you just do a random scan, the reconstruction algorithm cannot find all the atom positions. By the way, this also works when you just do an interlaced scan, but I just don't show the data here. But what came out was actually quite interesting, and that may be actually something to explore in future versions of such adaptive scanning. While the random scans, these are the green positions, they're somehow all over the place. The optimized or the adaptively, these optimized scan positions, whereas they're here still very random, they now actually converge to be positioned on the atoms. So it really seems that if your beam is positioned on an atom, it produces, of course, stronger scattering and more information than if the beam is between the atoms for these 2D materials. I'm only talking about such the sample right now. And that is actually interesting because this could lead to a much simpler adaptive scanning scheme, if you think about it. Now, the question is, I already mentioned that the data for this one experimental data set was reduced to only 144 numbers per beam position. And the question is, can we reduce the number of probe positions even further? And that is what a bachelor student in my group, Anton Ladyshev, has tried. So he did some simulations and simulated some Ptychography data from a dislocation model like this. And here you can see a high resolution image being simulated. Here you can see a single slice Ptychographic reconstruction. Actually, you don't really see the atoms very nicely. And the reason is because the accelerating voltage was set to 60 kV. So this is, even though the sample is only 9 nanometers thin, 60 kV is a very low accelerating voltage leading to strong multiple scattering. And of course, if you then use multiple slices in the reconstruction, you get a faithful representation of the atomic positions. Interestingly, the beam was only positioned every 1 angstrom. So in contrast to many of the ptychographic experiments where the beam is positioned much more finely, for example, 0.2 angstroms or so, here in the simulation was only basically positioned every 1 angstrom. And that was barely enough to resolve, in principle, in an image, the distance between these 2 silicon columns here. But if you then keep only 36 numbers for each probe position, you still get pretty much the same reconstruction. So you can really reduce from 500 by 500, so 250,000 numbers in a diffraction pattern to only 36 numbers per probe position, and being sampled only every 1 angstrom. This is actually just a few hundred kilobytes of data, not even a megabyte. So really, data can be reduced enormously and still get a 3D reconstruction going. And this is now applying this also to experimental data that was acquired on the spectrus detector on our microscope, trying different ways to compress the data. So this is basically what was shown in the simulation, 36 Zernica masks basically being applied to the diffraction patterns and then only storing the mask applied to the diffraction patterns. Or here reducing, basically doing the spinning approach that was applied in this data by Dave Muller's group, using 45 numbers per bright field disk, led to reconstructions where you could see really the atomic structure of the unit cell, but you didn't see any variations between unit cells. That means low spatial frequency information was missing. Also the probes, this probe corresponds to this reconstruction. This probe here, which clearly contains specimen information, corresponds to this reconstruction. So that didn't work so well. But if you really apply masks that are based on just sampled diffraction patterns, so before you do your experiment, you just sample a few diffraction patterns, you orthogonalize them and use these as masks, the probe also gets reconstructed very nicely, in addition to the sample reconstruction being much more faithfully retrieved. I have a few minutes, just like 6 minutes or so left, to show you really what I mean by next steps. So in this workshop, you have seen a number of very nice and attractive algorithms that people also then make available online for download. I don't know how many people actually then follow up and download this and are able to make this working on their system. So the question is really, should we aim for a new type of, well, it's not so new because it seems that also other groups have tried this, but at least I want to show you about our activity towards developing a data infrastructure that allows people to really enter this field of applying advanced algorithms at a very low threshold, basically just getting in, testing things on their data without having to deal with installing software and so on. And there is more behind it than just that, because, and I'll show you one example here. This is just a motivating example, not in ptychography or diffraction mapping, but in yields. What you see here is the dielectric function, reconstructed using actually quite an elaborate chromosphonic reconstruction algorithm, which also takes into account relativistic effects. So it self-consistently corrects for things like Cherenkov radiation, guided light modes, and so on, that are all defined in the Kröger equation, but to actually get them out of the data really means you do have to do some iterative refinement. And if you want to apply this to mapping, it also needs to be GPU enhanced and so on. So this is really Alberto Ferrat in my group. He really invested a lot into this to make things possible, like you see here, for example, recovering the dielectric function of, in this case, barium stannate, both the imaginary part and also the real part of epsilon of omega. And interestingly, then there was a group in our department by Claudia Draxel that now did different DFT calculations. So a standard DFT calculation and also an all-electron calculation using her own code, solving the beta-side-beta equation. And you can really see if this improved theory is applied, it really agrees very well with the experimental data. So having this capability of having an experiment that you can then compare with theory and also somehow feed the theory into your experimental reconstructions is actually something that I think is around the corner. I mean, this is what will be applied more and more, where these actually theory and experiment converge, because now we can really describe the same systems with all the computational power that is at our fingertips already. And so what would be very important now is to really have an infrastructure where this theoretical and experimental data can really be compared directly and can be shared. Let me give you another example, not in my field, but it was in the news a year ago. AlphaFold was able to predict the folding of proteins just from their sequence. And they did this very successfully, much, much better than any other of the contestants in this year-long contest of groups trying to solve this problem. And what they did, of course, they developed a very advanced artificial neural network, and I give them full credit for this, and I don't understand everything that they did. But what I understand is they couldn't have done this without relying on databases. So there was database information about the 3D structure of proteins, both solved by X-ray diffraction and more recently also by electron microscopy. And if you look at the submissions to this database, it started already in the 1970s. And so this was done in 2021. So almost 50 years after this database started to collect data, this data was actually used for this great breakthrough. And I'll just show again this one. This is now the submissions on the scale of, this is now 2,000 submissions per year. Initially, of course, there weren't so many yet. But with the number of years, this actually increased steadily. It's now stalling or actually decreasing a bit again. And the reason for that is because there is another technique, another cryo-electron microscopy that is picking up. But that actually shows a very important point, because this database is now apparently able to deal with data from very different sources. But the point I want to make is having such databases of information about materials, in our case, in this case, it's proteins, is going to be very valuable. I mean, we see that machine learning techniques really take over all areas of our life and also material science. That's why we should really start to collect this type of data. And just to show you, again, here's another database, for example, of yield spectra, because I just was talking about yield spectra. There needs to be also a driving force behind it to keep these databases growing. I mean, this database, this yields database, was established I would guess about 10 years ago. It still contains only 287 spectra. So it hasn't been growing for many years. And the reason, of course, is there needs to be also some resources behind it to keep things advancing. Here's another open database, which seems to keep growing. And the reason is also because it's more generic, because crystal structures can then be used in all kinds of different contexts. And the question is also, how reproducible data is. If you have yield spectra, you don't know so much about your experimental conditions. If you have crystal structures, that is something that everybody can relate to. You can now simulate all kinds of different experiments from this. I just wanted to draw this background to explain to you one project that is very where we invest actually quite a bit into. So in Germany, and I know there are similar initiatives also in other countries, I'm just talking about our country right now, the government has decided, let's invest 1 billion euros in basically investing in such consortia, which then somehow develop a national research data infrastructure in all kinds of fields. So this is including archaeology and so on. But also, one of them is for material science, and that is PERMAT. It's actually chaired by Claudia Draxel, a colleague here in our department. And so there's very strong link to this project. And one of the aspects of this is also somehow developing infrastructure for experimental material science. And initially, we focused on only 5 techniques, which among ours, optical spectroscopy, XPS, atom probe tomography also include electron microscopy. And I see my time is slowly coming to an end. I just want to show you this infrastructure that is now developing, where we really use electronic lab notebooks and databases to process data also online. So just let me give you a quick example. So you can upload data by dragging into it. And this is now just a quick video showing it's sped up by a factor of 4, showing that you can now run directly on the server, even like interactive software, like in this case, it's Neon Swift, where you can really look at your 4D STEM data, and you can also then do some center of mass analysis, and you can extract spectra. So all the interactive work that you do with your data on your desktop can now be done basically on the server. And the server is actually something that you can install in your own lab. So you keep control over your own software, but of course, in the process of using the system, you make your data also available to be uploaded into a database where this data can be shared because it is well documented and so on. And you can apply scripting commands to this, of course, within the software. And in addition to using this software tool, you can also use more generic tools like, for example, Jupyter Notebooks, where you can really now do this typographic reconstruction using a Jupyter Notebook. Just you can explore the data, for example, looking at these few coefficients per probe position only, and then run a Jupyter Notebook that you submit yourself together with the data. And that is now being done right here. You just click on launch, it launches. And if there's some library that you still need and that's not provided by the system, you can simply install this library by doing a pip install directly on the fly, and basically get all the tools, for example, HyperSpy and so on, being installed, and then run your reconstruction, watch it live, and look at the results at the end. So I will not go to the very end here, but I want to come to a conclusion. So I believe electron microscopy has become more indirect. So we don't look at some phosphor screen anymore so much and try to interpret data that we see there. But computers are really becoming more and more part of the process of recording this research data. And we need to watch out that we don't collect too much data, but try to really work on compressing data more and more, because there seems to be a lot of redundancy for many of the things that we want to extract. And the last point here, really sharing your valuable reconstruction algorithms as online tools will give you a broader audience and will also give you more feedback, and will also, I believe, be easier, and it will spread your work more than if you just provide links, for example, to GitHub repositories. Thank you very much for your attention.